Hello, this is Kerry Schutz with MathWorks, and in this video, I'm going to show how to use Simulink and Simscape Electrical to model and simulate a buck converter. So what we're looking at on the screen now is essentially what I'm going to build up. We're going to build up the buck powertrain in some fashion. We're going to model the PWM. We're going to model the closed loop nature of the control system, a load disturbance, things like that. And then we're going to exercise the model, simulate it. And so let's just do that. Let's jump right in. Okay, so now we're over in MATLAB. I'm using R2023B, and we're literally going to start with a blank sheet of paper here. So I'm going to say right click and say new model, and that will give me an untitled model. I'll just call this buck test 1 for buck converter test 1. I'm going to double click on that model to open our blank sheet of paper in Simulink, our blank model canvas. And now it's time to just start bringing in components. So the first thing I'm going to do is just click in the white space of the model, left click and type in IND, inductor. And with that, I typed IN, it says, okay, do you mean this or this? I say inductor. And I can start doing that for all of the components. I'll just do the same thing for capacitor. I just left click and type CAP and then just bring it in. Then I'll do the same thing for my load resistor. I'll type RES, bring in the load resistor. Now, from here, you can start laying out the components in the orientation you want. I'm going to hit Control R on my keyboard to rotate them the way I want them and just start laying them out. You can start connecting lines or wires from node to node. If I want to bring in an electrical reference, I'm just going to type EL, do this, connect that up like so, like so. Now, of course, if you're new to Simscape or Simscape Electrical, you may be asking, well, I don't know what to type. I mean, maybe it's easy for resistor and inductor, but what about other things where we're not typed in? And that's what the Simulink Library Browser is for. You can just click on the four colored squares. It brings up your library browser. By default, it's docked into your window. If you want to look at it outside of that as undocked, which I tend to do, I'll just close the dock version. Then you can go over here. You can look at your base Simulink sublibraries that are things like continuous systems, discrete systems, logical and lookup tables and matrix and math operations. But I'm using Simscape right now, and specifically the Simscape Electrical subproduct under Simscape. So Simscape is a family of physical modeling tools, and then electrical, and other domains are underneath it, like hydraulic, etc. I am going to just look under the electrical sublibrary under passive, and from there you can start seeing components like capacitor, which you could drag and drop in. Where is the inductor? They're in alphabetical order, so you can say IND inductor. You could just drag them in that way as well. And finally, if you're in the Simscape library browser, you can also just start typing in things like IND, find everything that's an inductor, and it'll go off and search through all of the Simulink libraries that you have installed. I have quite a few here, and it'll find everything that has the word inductor in it. In this case, you can see there's quite a few. I'm just using the base one, you could say, from Simscape, or the one from Simscape Electrical. And the difference here, there's actually two here listed that look identical. One thing just to learn about Simscape is there is one of these blocks comes from the base Simscape component library. The other one comes from the Simscape Electrical. So they look identical, but if you double click on them, you can see some differences. So that is one of them, and then I'll bring the other one on top of it. Oops, actually I didn't mean to minimize that. We'll open up the second one as well, and we'll put them side by side. And what you'll see is that the base Simulink one just has inductance, series resistance, parallel conductance, and a few things for initial targets and nominal values. If you get the one from Simscape Electrical, then you get a few extra options. You can select the tolerance, you can select operating limits as well, and faults. So there's a few more power features associated with the Simscape Electrical version of it. So it's a superset of the base one that comes from the Simscape Foundation library. And that holds true for many of the components, not just the inductor. Okay, so for right now, I think I use the Simscape Electrical, the more elaborated version of the component, although I'm not necessarily going to be using all the elaborated features. All right, so this is, the core part of my buck powertrain, the inductor connected to parallel combination of the series of the resistor and the capacitor. Okay, so a few more things, obviously we need to do here. I'll move this around, select it, shift it to the right. I'd probably like to sense my voltage at the output, so I'm just going to type voltage sensor. And this just, again, I'm not going to the library, because once you get used to using Simscape and Simulink, you'll just remember the names. You can just type them, bring them in quickly, as opposed to searching through the library and dragging and drop. All right, so now I've sensed the output voltage. I also need to drive the input with something. That's going to be where my PWM comes into play. So I'm going to type PWM, and it just so happens that Simscape comes with a PWM generator. Of course, you could also create your own version of one, but I'm just going to use the one that's there at my disposal. And of course, all these blocks are parameterized. I haven't gone into these blocks yet. We're going to lay the model out architecturally first, and then we'll go in and parameterize and set its particular settings later. All right, so we're going to implement a synchronous buck converter in this case. So that means I'm going to have a high side switch and a low side switch. So I'm going to bring in, instead of modeling this as a MOSFET switch, I'm going to just bring in an ideal switch in this case. And that's not the one I wanted. Let me just type, there's many, again, switch options as well. I'm just going to bring in the one from the base library of Simscape, and I'm going to have, this is going to be my low side switch, so I will connect that up to the inductor here. The other side will go to ground. And for the high side, I'll just drag and make a copy of it. And this will go to the high side, and this will go to my input voltage. And for the model of the input voltage, I'm going to bring in a DC voltage source from Simscape. I'll connect that up here. And I would also, like a ground for it as well. So I will bring in fact, I'm going to rotate that voltage source around a little bit like this to make connecting the ground a little easier. I'll just drag another ground over here so I don't have to wire it very long. Okay, so that's my input voltage. You call that VN in some cases. All right, so what about the PWM? Okay, I've got my high side, I've got my low side, but now I need to drive that with PWM output, which is here. Now it turns out that this block is a unidirectional Simulink signal output, while my circuit over here, these signals are not unidirectional, they're bidirectional. They're current voltage, they're physical signals. So we cannot connect a Simulink signal line directly to a physical signal in Simscape. What we have to do is convert it first. So I'm going to bring in what's called a Simulink. I'm typing this. You left click and type a few letters of what you're looking for. A Simulink to PS converter. It's from the utilities library of Simscape. So I'm going to bring that in and connect it up right there. Again, if we go back to the Simulink Library Browser, let's see, did I leave the full undocked version open? I did. I don't need this one. We could go under Simscape Electrical Utilities. Actually, it's under the base utilities under Simscape, not the other one. And you'll find in here a physical signal to Simulink converter and a Simulink to physical signal converter. So these are the two I'm going to be using to go back and forth between Simulink and Simscape. Very handy blocks. All right, so that signal is going to drive, let's say, my high side, but I need to also have a low side signal, and there's many ways. In this case, I'm just going to manufacture the low side signal from the high side, and I'm just going to use a logical inversion to do that. So I'm going to pull in a logical operator, and in this case, it's going to be a NOT. And let's just bring it here, and that's going to go again over here. But again, you can't do that directly because we are going to need that physical Simulink to physical signal converter over there. Now, one thing to keep in mind, and again, we're not modeling this buck converter in great detail. You notice already over here, I've used ideal switches that just have, modeling like an RDS on kind of on resistance, as opposed to an actual MOSFET parameterized component. the same holds true with the PWM. I'm not modeling it at a high degree of fidelity where we'd be modeling, dead time and slew rate, maybe all the details that might be associated with that in practice. I'm keeping it simple right now. Um, and we could model those real world effects, but again, in the spirit of just keeping it simple when you get started, I'm skipping over some of those details, also for the sake of speed in this video. So anyway, we want to drive the output on the low side with the inverted signal, the complementary signal that we're driving the high side with. And a simple inversion will do that in NOT operator. Again, not a circuit NOT operator, just a behavioral NOT operation in Simulink. But we can't, this is a kind of like a quote unquote logical signal. And over here, we're driving this kind of analog real world thing. So we can't drive logical and real. So we have to do what's called a data type conversion here. So I'm going to left click here and type data type. And then of course it just, looks for everything that starts with data. And then I clicked on the wrong one, so I have to do it again. Data type conversion. We'll pull that in right there. And now we will drive that there. Let's see, did it not accept it? Let's try it again. Yeah, there it goes. All right, so now we're driving the low side with the complementary signal. We're driving the high side at. This will go to ground. I could connect it over here. I connect it any number of ways. And now we've got the basic setup here. Now, of course, my duty cycle input, again, that's duty cycle input, not direct current DC. I'm going to manually just pull in a fixed duty cycle right now as a constant block in Simulink. And duty cycles, of course, can go between 0 and 1. So I'm going to use something like right in the middle. Let's just say 0.5. And now we're set up where we actually could run a test. So let me pull in a scope, because you always have to have a scope in your models to see what's going on. You need some kind of visualization. So let's pull that in and connect it up here. Now, there's another problem here that we're running into, that you just simply can't take a physical signal and run into a scope. You also have to convert that back to a Simulink signal from a physical signal. So I'm going to just type here PS, physical signal, and it says, yes, physical signal to Simulink converter. Connect that up here. Now we can drive the scope with this unidirectional Simulink signal that knows nothing now about currents and voltages on the right side of that block. Now I could hit play at this point. It turns out that I am going to get an error if I do that. I don't want to do that anyway because I haven't set up any of the real parameters in this model. I've just used the default. So I definitely want to set reasonably intelligent parameters before I hit play, and also want to set a realistic stop time. Okay, so another thing I need in this model is also basic infrastructure to run the Simscape portion of this model, which is called a solver configuration block. So I'm going to just type solver. And again, you'll find that like utilities, the same place I showed you earlier in the Simscape library family of blocks. And if you like to pretty things up, you can always drag blocks around and rearrange them, slide them over, so on and so forth. This block, by the way, doesn't simulate, it doesn't consume voltage or current, it doesn't generate a voltage or current or consume any current. It's simply there to tell Simulink that it's Simscape and it could have its own, it could use its own particular solver settings. In this case, I'm going to be using the Simulink global solver to simulate the Simscape circuit, but you could click here and use the local solver with a particular sample time. I'm not doing that here yet. All right, but it still needs to be there in any case. It's a matter of logistics and infrastructure, just a checkpoint. So now let's start setting up some parameters on the model. Let's say I've got a 30 volt input voltage on my buck converter, set it to 30 volts. Let's say my inductor is, I don't know what I want to set this to. I'll just make it a whopping 1 millihenry in this case. Let's set our capacitor to be about 47 microfarads, large capacitor, and a very small load resistance of about 2 ohms. And let's just go with that. And let's see, anything else? Oh, I haven't set any PWM parameters. Let's say I've got a 50 kilohertz switching rate, and I have I'll say it's a continuous time PWM. So I'm not modeling as a discrete, I'm modeling as continuous time circuits. And I think we're set to go. Let's go ahead and bring our scope up so we can see the progress as it goes. Let's see, where is it at? Here it is. Put it off to the side here. I'll make my model a little smaller. And this is a 50 kilohertz switcher. So I will run this at 50 E3, 1 over, that would be 1 cycle. Let's run it for 1,000 cycles, 1,000 switching cycles. Let's see what happens. See if I made any mistakes or getting any sensible results here. All right, it's running, and I'll auto scale it. It looks like it ran up to about 15 volts, which for a 30 volt input and a 50% duty cycle, that should come out to be about 15 volts, and that looks about right. Okay, so I've got my PID block in. I'm going to resize it. And because it's going to be in the feedback path, I'd like to flip the blocks basically horizontally such that they kind of face or operate from right to left rather than left to right. So you could just rotate these blocks to do that, but there's another way which you might find more handy, and that's just to draw a wire in the feedback path and draw the block over the wire, and it automatically reorients the block as well as moves the label. So that's handy. And then of course we want to connect this up here. We could just, delete this line, connect up the new duty cycle from the PID, and be done with it. Or we could say we want to run in both open and closed loop. We kind of want to be able to, the flexibility to go back and forth quickly between the two modes of operation. So I'm going to do that. Just put that in there, wire it up, however you like. You can move blocks around to align things nicely. And at that point now, okay, at least we've closed the loop. Now, of course, we'll want to be able to limit that duty cycle to be, between 0 and 1, or 0% and 100% on time. So I'll pull in a saturation block for that purpose, and I'll just connect that up as well. And let's say it'll go from 97% on time to 3% minimum on time. And of course, we need to have some type of reference that we're going to be comparing against. So if we're a little bit too high voltage, we want to generate a smaller duty cycle. If we have too small a voltage, we need to increase the duty cycle. So in order to generate that error signal, I'm going to, first of all, pick a reference block. I'm going to say a constant block. In this case, a constant voltage. Serve as our reference. Do the familiar Control R to rotate it. Move the label from top to bottom. That will feed into a subtract block. We'll reorient the subtract block likewise, move the label down. And that, now, here's another little detail here. You could say, well, this is going to be negative feedback, so I'll just connect that there, and the reference voltage go here. But then you got these crisscross wires. It's not as pretty or intuitive. So let's not do that. Let's just change the ordering of the signs. I'll go from, instead of plus minus, we'll go minus plus. Negative feedback always. Okay. And we're going to call our reference voltage 15 volts. If we wanted to ramp that voltage up from 0, make it a gentle on ramp, which in practice you probably want to do instead of a hard 15, we could do that as well. Just not showing that model elaboration here just yet. All right, so our error signal will feed the PID. I haven't showed you anything about underneath the hood of the PID yet, so let's double click on it. We could run this PID in continuous time or discrete time mode. If it's discrete time, we need to pick a sample time. I'm doing the simpler mode, continuous time. I'm going to set a proportional gain factor of just say 2, an integral gain factor something larger like 20. I'm not going to have any derivative gain, potentially speeding up the response. Just leave it there. So no derivative, just PI in this case. Say apply, okay. At that point, we should be good to go. So again, this was our, if you take a quick mental snapshot of this, this was our open loop operation. I'm going to toggle it to closed loop operation and run for the 10,000 switching cycles and see how it does. Now there is going to be a problem. I can see this occurring already. It's running very, very slowly. Now it is producing numerically sane or valid results, but it's just running very, very slowly. So I'm going to stop it here and take a heed of a warning down here. It says view to warnings at the bottom of the Simulink model. It's a little hyperlink or a little link you can click on. It'll tell you what's going on. It says it found an algebraic loop. Block diagram, buck test 1 contains one algebraic loop. See more details about the loop, use the command this or the debugger, or you can just say, you know, where is this algebraic loop? It says it consists of these blocks, and without going through and clicking all those blocks, I can tell you that it is the main outer loop, the PWM generator into the powertrain, into the subtractor, into the PID, into the saturator, and back to the PWM. So there's a zero delay, or algebraic loop is by definition a zero delay loop, which is a physical impossibility. It's non-realizable. And so we want to address this, A, because it's non-realizable, B, because it slows the model down substantially as it has to solve this algebraic loop repeatedly at each time step of the simulation. So let's do that. One way to break a loop like this, a zero delay loop, is to insert a very, very small kind of infinitesimal type of delay into the loop. Of course, our goal here really is to model reality as close as possible. So what I'm going to do is just say there's some type of circuitry or measurement delay on the voltage measurement, the output, and I'm just going to model that. So I'm going to pull in, instead of a finite, perfect delay, I'm going to pull in something that would have a group delay associated with it. I'm going to pull in a single pole low pass filter. Of course, we could describe this to be of any order. And I'm going to place that single pole at 10 megahertz. Since this is specified in radians per second, I'm going to say 10 megahertz, 2 times pi times 10^6 for the single pole low pass filter cutoff, or 3 dB points. And now we can see that. Now let's run it again and see if it runs faster. It should. And yeah, it's running much faster. And you can see the response also looks different. These pulses are much smaller, and they're much shorter duration than they were when we ran in open loop. And that, of course, is a good thing. We would hope that our closed loop operation was better, an improvement over our open loop operation. We can, of course, zoom in on that and see as well. Let's just do that. And yeah, we can see where the voltage is and so on. Okay, so it doesn't look too bad there. Okay, these pulses are, again, smaller amplitude and shorter and less energy in the pulse. All right, now one thing you might be curious about, this kind of begs the question, what if you want to look at both signals, both the open and closed loop side by side? That would require some amount of, you could, of course, have two implementations, open and closed loop, in the same model running at the same time. Of course, that's going to consume more cycles and eat up more screen real estate. Or you can just time multiplex and run one each simulation and overlap them. One easy way to do that is to log the data at the node of interest, let's say the V out. And of course, we could also just rename our nodes also as a form of just, description, annotation. We could just name it accordingly. I'm going to run it again. First of all, I'll do the open loop simulation first. This means log the signal, that little Wi-Fi like symbol. Let's go ahead and log it. Take a few more seconds to run. And we can double click on that signal, on that Wi-Fi symbol, logging symbol, when we're done. And it's going to show us our output here. Now, you do want to be careful when you open up Simulink Data Inspector, because now there's different types of plots supported. You want to make sure this says time plot, generally speaking. You could also see array plot and other types. You want to make sure it's the type that you desire. Otherwise, the visualization may not be what you had planned. All right, so let's run it again now in closed loop and see, just overlay them. We can also run this from the model with this play button. We can run it from the scope with this button, or we can run it from Simulink Data Inspector with this button right here. Okay, so I don't know, it doesn't really matter. We can go ahead and run it right here. Oh, let's see, did I do that right? I guess I didn't. Let's go back and just run it in the Simulink model then. I guess I'm mistaken there in terms of my statement on playing the model from Simulink Data Inspector. So we're running it again. Now we can definitely see a difference there. And what I'm going to do now is go to my archive. I'll call out the previous one we just ran. I'll enable that. We'll overlay them. And I'll make them different colors since they are. So I'll call the first one, we'll make it red. We'll just click on that and make it red. We'll make the second one green and set. And now we've got them overlaid, and you can see red is the open loop and green is the closed loop, and we can see the difference between them in terms of the amplitude size and the amount of just energy in those pulses. All right, so I better call it there. My recording is getting kind of long. This is really just to serve as my introductory video on building up Simulink and Simscape models in particular. And then I can, do some more videos on follow-up to add more, how you would add more details, fidelity to these models and more automation. So look forward to that in the future here to come. Thank you.